Hi there, this is the overview of our project. We implemented multimodal survival predictions in glioma by integrating MRI and clinical data using convolutional neural networks. I'm Ning Huihao, and my other group members are Qianwen, Shuhua, and Taiyang. Glioma is a life-threatening brain tumors. The traditional prognosis model is solely based on the clinical data, while currently available 3D magnetic resonance images provide a rich, detailed view of tumor structures with additional insights. So our project aimed to integrate clinical data and MRI data as inputs to the neural networks to predict the patients. The dataset we use is from UCSF, and the clinical data mainly contains age, gender, tumor graders, and genetic markers, while 3D MRI data are focused on tumor region of glioma. For data pre-processing, after splitting dataset with the proportion of 0.2, we check and fill the missing values. For more details, please refer to the notebook. We also ensured that the balanced number of cases, scale numeric variables, and one-hot encoding categorical variables. We then checked the correspondence of two kinds of data, and manipulation of images are mentioned in the later part.
Through EDA, we find predictors associated with survival. For example, high tumor grades is associated with death, and higher MG index is associated with survival. Through PCA, we find clusters of dead patients, which indicates the predictive power of the clinical data.
Another important data is the 3D MRI image with its tumor segmentation results. Naturally, we want to include only the tumor part, which is more related to the survival outcome. Additionally, the data is very large. We first performed 3D max pooling to decrease its resolution, and there are two other strategies that follows. One is to collapse the 3D into two-dimensional data, and the other is to resize the 3D data to include only the tumor part. So this gives us some flexibility in addressing the model choice. For example, for 3D, we could perform 3D convolution neural network, but it's very computationally expensive and its performance is not ideal. So we would transfer to 2D convolutional neural network. But we might want to add clinical data. So we want to learn a low-dimensional representation of the data using an autoencoder and to combine it with the clinical data. But then we find that ResNet50 transfer learning with 2D image alone performs quite well. So we want to use the transfer learning outcome and combine it with the clinical data to combine the model. So this is how we arrived at our final model.
Move to the baseline model part, which is a simple 2D CNN structure. It has 4 convolutional layers, a flattened layer, and 4 dense layers. Obviously, we can see that the model is overfitting to the training and validation data. We can also see that there are some fluctuations between the epochs in terms of validation accuracy, which indicates that the model is unstable. To improve the model performance, we moved to transfer learning of the ResNet50 model on the 2D image data. It is pre-trained with ImageNet and has 50 deep layers. We added global average pooling and 2 dense layers on top of the model. Firstly, we trained the topping with a normal learning rate. Secondly, we fine-tuned the whole model with a low learning rate. Obviously, we can see that the model performs better than the previous model with less overfitting. Interestingly, although the validation loss goes up, validation accuracy also goes up and stays stable.
Our final model achieved impressive training accuracy of 94%. However, on the validation and test sets, the model exhibited an accuracy of 63%. This suggests the model generalizes to new data but has a risk of overfitting. Looking at the confusion matrix, we observe 31 true positives and 31 true negatives. The model has a balanced performance in correctly identifying both survival and non-survival cases. On the test set, the area under the receiver operating characteristic curve and the precision recall curve suggests moderate prediction ability. A classifier using only clinical data achieves an accuracy of 60%. Our model outperforms this baseline, highlighting the added value of incorporating images. In conclusion, the multimodal transfer learning model has the best performance among all models. It shows moderate ability of prediction. Using both clinical and image data contributes to accurate prediction. Moreover, the model has a risk of overfitting.
In the future, we could implement 3D CNN model and also try autoencoder to learn both images and clinical features. For data aspects, including more detailed image analysis and more granular clinical data might improve the accuracy of our predictions. And that's all. Thank you.